All right. So we're going to talk a little bit now about what we call solutions. Solutions. Solutions are homogeneous mixtures. Now, remember back when we talked about homogeneous mixtures?
Yeah, I remember homogeneous mixtures.
And what was homogeneous about the homogeneous mixtures?
Homo means same.
Yes, that's right. Homo means same. And what was the same about those homogeneous mixtures?
They had like the same concentration throughout.
That's right. So if I have a solution here, right? And let's say it's a solution of water and sodium chloride. If it's a true solution, then the concentration, the amount of water and sodium chloride at this point will be the same as it is at any other point in the solution. That would be a homogeneous solution. If I put so much sodium chloride in there that there began to be a pile at the bottom, then the concentration of sodium and chloride in water here will be different than the concentration of sodium and chloride in water there. And then it becomes a what?
Heterogeneous solution.
That's right. Heterogeneous mixture. And solutions are homogeneous mixtures where there are what we call there is a solvent and a solute. The solvent's the thing that's in the highest concentration. The solute, or there could be more than one solute, are the thing that's in the lowest concentration. This is an example of a solution of water and sodium chloride. Water is the what? The solvent or the solute?
The solvent.
That's right. And then the sodium chloride is the solute. We can also have solutions of, for example, this is a balloon full of air, okay? And it can be a solution. What's in that solution?
Um, well, air.
That's right. And what's in air?
Oh, it's nitrogen, oxygen, and carbon dioxide and argon.
That's right. So nitrogen gas, oxygen gas, argon, carbon dioxide, those are the four major components, right? 80% nitrogen, 20%, 19.99, less than 1% of anything else, right? Just very, very small amounts of the rest of the stuff. So, what's our solvent in air?
Oh, is it the nitrogen?
That's right, because it's in the highest concentration. What are our solutes?
Oxygen, argon, and carbon dioxide.
Very good. So, solutions. Concentration refers to the relative amount of our solutes in solution. All right? And we can express this a variety of ways. Okay? Dilute or concentrated. Those are two words that you're probably familiar with. Not a lot of solute for solvent. That's dilute. Concentrated, more, right? And we could say a solution becomes saturated. And sometimes people use the word for concentrated to say that it's saturated. It can't take any more solute. We just talked about this picture of our solution of sodium chloride in water. If we add too much sodium chloride, it becomes saturated, and we get a pile of sodium chloride on the bottom. So we can saturate it, right? Unsaturated means it can contain more solute, and there's a scenario that's called supersaturated, where if you slowly dissolve a compound, it can actually reach above, the amount that's dissolved can be above its solubility. This is often done by raising the temperature as well of a solution, the solvent, right? Because solubility, the amount that's actually able to dissolve, is temperature dependent. And then the way that we express the concentration of our solutes in solution, the preferred way is what we call molarity. Molarity. It tells us how many moles of solute there are for every liter of solution. All right, this is what we call molarity. So going back to our example of a solution of sodium chloride, if I have 1 mole of sodium chloride, now Fred, do you remember how many grams there are per mole of sodium chloride?
Well, I don't remember, but I can figure it out with the periodic table.
All right. So,
Sodium's 23, chlorine's 35, 58?
yeah, so about 58, 23 plus the 35.45, so 58.45 maybe. Okay, so there's 58.44 grams for every mole. So if I have 1 mole of sodium chloride, or 58.44 grams of sodium chloride in this bottle, okay, and it's filled up with water to make a total volume of 1 liter of solution. Notice I didn't add a liter of water. I added enough water to fill it up to a liter. Okay? So there's 1 mole of sodium chloride dissolved within this liter of solution. And that means that, again, there's 1 mole of solute for every liter of solution. I say I have a 1 molar solution of sodium chloride. So it's 1 molar sodium chloride. Also, just capital M NaCl. 1 molar sodium chloride means I have 1 mole of solute for every liter of solution. 1 mole of sodium chloride for every liter of solution. This is 1 liter of solution. Over here, I have a different bottle. It's also 1 liter large. Okay. There's the 1 liter mark. But I only have it filled up half the way. It has the same solution. I poured that into here, but I only filled it up to 0.5 liters. Notice that in this solution here, I have some sodium chloride, right? Some sodium ions and some chloride ions. They're dissociated, so I'll write it like that. And I have some water molecules, okay? The total volume of the solution is now what?
Half as much.
Which is how much?
0.5 liters?
That's right. I have 0.5 liters. How many moles of sodium chloride are in that half of a liter?
Well, I don't know.
Well, it's half as much, right? Because there was 1 mole in this whole thing, and I put half of it into here, so now there's a half a mole in there. So I have 0.5 moles of sodium chloride for every 0.5 liters. But the ratio still ends up being the same concentration. So molarity, or concentration of solute per liter of solution, is an intensive property. It doesn't matter how much of the material you have, its concentration is the same. Okay, so here's another example. Molarity of HCl in a solution is 6 molar. That means that there's 6 moles of HCl for every liter of that solution. That's molarity. Okay? So, what is the molarity of a solution that's created by taking that much potassium nitrate and enough water to make 350 milliliters of solution? Notice again that they didn't say we added 350 milliliters of water. We said we added enough to make 350 milliliters of solution. Okay? So, 10.2 grams of potassium nitrate. I can identify how many moles that is. Oh, look, they gave us the molar mass of potassium nitrate there. And I can identify how many I can identify what the total volume is. So I can get moles of solute, total volume of solution. What is the total volume of this solution?
It's 350 milliliters.
Good, 350 milliliters. Do you know how many liters that is?
1,000 mil. Is it 3? Oh, I can't remember how to do that.
Well, if I have 350 milliliters and I want to go to liters, right? Milliliters need to go here and liters need to go there.
Okay, so there's 1 liter is 1,000 milliliters.
Very good. 1,000 milliliters. So 50 divided by 1,000, that's 0.35 liters, right?
Yeah, okay.
So I have 0.35 liters of solution, 10.2 grams of potassium nitrate, right? 10.2 grams of potassium nitrate. And I want that to be in moles of potassium nitrate, right? Because if I can find my moles of my solute, my liters of solution, right? Then I can put the moles of the solute over the liters of solution and get my molarity, right? So what's the molar mass of potassium nitrate?
101.1.
Okay, and you got that from this down here, right?
Yeah.
So 101.1 grams of potassium nitrate for every 1 mole of potassium nitrate. Whoops, there we go. So 10.2 divided by 101.1. And the answer is 0.101. That's how many moles of potassium nitrate I have. Okay, so 0.101, and that's how many moles. This is how many liters. I can go 0.101 moles of KNO3 divided by 0.35 liters of solution. So here, divided by my, I didn't calculate that, I just did it in my head, so 0.35. And my total solution will then be 0.29 molar. That's a big M, right? 0.29 molar solution, which, what does molar mean?
Moles per liter.
That's right. Molar doesn't mean moles. It means moles per liter. Now let me show you a different way that we could think about this one. And this is the preferred way to answer this problem. What we're going to do here is we're going to say that I want my the units I'm after, and the units I'm after here are moles of KNO3 for every 1 liter of solution, which is molarity. All right. So they asked us what's the molarity, big M, and big M is moles of solute per liter of solution. I identified that that was the solute. All right. And so then I can start with 10 grams or 10.2 grams of KNO3. And I can go from grams of KNO3 to moles of KNO3. And then I can go from moles, oh wait, no, I want moles of KNO3 at the top, good. Now I just need to get my liters of solution down below there, and I can just plug those right in, 0.35 liters of the solution. So it's all in one combined calculation, 10.2 divided by, oh, this was 101.1. Divided by 0.35. All right, so same thing that we just did, but we can keep it all in one statement here. And we can show whoever we're trying to explain this to that I took my grams and converted it to moles, and then I divided my moles by my liters of solution, because that's what my units that I wanted were moles per liter. So I got the molarity of my solution. We can also identify, for example, the mass of potassium nitrate found in a certain volume of a given molar solution. Same thing here, equal sign. What goes to the right of my equal sign, Fred?
You're after the mass. Grams?
Grams of what?
Potassium nitrate.
Very good. Grams of potassium nitrate. After mass there, and we start with?
You start with the 25.33 or the 0.05?
You can start with either one, and that's not a problem if you start with something that's wrong and you get halfway through and you can't figure out, you just start over. Try something a little bit different. Which one would you like to start with?
Well, the 25.33 is fine.
So if I say 25.33 milliliters of the 0.5 molar solution, what can I go from there?
I don't know. What do you do?
Well, I want grams, and I'm given molarity. Now, what does molarity mean?
Molarity, I can't remember.
Molarity means moles per liter. It's a concentration. It tells you how many moles there are per liter of solution. So if I converted this to liters, then I could identify how many moles there were for every liter that I was provided. Does that make sense?
Not really, no.
Well, watch this. If I go from milliliters to liters, now the reason I did that is because I was provided molarity, and molarity is moles per liter, right? So then I can get rid of liters with this molarity and identify how many moles of potassium nitrate there is for every liter of solution. So I went from milliliters to liters. 1 liter is 1,000 milliliters. And then I go from, milliliters are gone, right? I go from liters to moles using molarity. The solution's concentration is 0.05 moles for every liter. But I can also say that there's 1 liter and it contains 0.05 moles. Okay? Just like the density, this can be expressed either way to be utilized to answer whatever problem we're after. So I put liters on the bottom and I put moles on the top. It's 0.05 moles for every liter of solution. And that's moles of KNO3. And now I want grams of KNO3, but I have moles.
That's just the molar mass.
That's right, moles of KNO3 and grams of KNO3. There's 101.1 grams for every 1 mole. So I have ended up with grams of KNO3. So 25.33 divided by 1,000 times 0.05 times 101. That should be our molar mass, our grams of KNO3. Okay, did you get that?
Yeah, I got it. That's pretty cool.
All right. It's kind of difficult for new students to realize that molarity can be expressed in terms of 0.05 moles per liter, but it also means that every liter of solution contains 0.05 moles of that material. Okay, good work.